My name is Saurabh. I'm an engineer on ML Platform, machine learning platform at Lyft. And today I want to speak a little bit about the technical decisions we made around building a scalable machine learning platform. I want to start by talking about problems that we're trying to solve, and then get into some of the details of how we approach the solutions. How many people out here have used Lyft before? Just raise hands, please. Okay, so most of the audience has. And so let's talk about the classic Lyft experience. You open your app, you're trying to put your pickup spot and destination, select a payment method, and call a ride. When this process, underlying this process, there's a lot of machine learning that's happening. We can smartly pick the pickup spot from a very noisy GPS data to know exactly where you might be. Then we can also do some predictions on what are the most likely destinations you want to go to, based on your ride history, based on your previous ride you took. We might be able to pick automatically a payment method if you have several of those. Maybe use a different card during commute hours compared to a business trip that you're on, or during weekend rides. We can run machine learning models to optimize what driver gets dispatched to you, or predicting the ETA of your ride from your source to destination, or picking up the right matching passengers if you're taking a shared ride. So every part of the experience has machine learning powering it. We have hundreds of machine learning researchers working on just the classic Lyft experience. Aside from that, we have a ton of people working on autonomous driving, using deep learning extensively for computer vision, planning, and mapping. So my team's job is to build out a machine learning platform that makes it easy to develop new models, prototype many different approaches to your machine learning model. Once you have a few models that you have selected, we want to make it easy for you to try out different training algorithms. For example, if you might want to tweak the learning rate on your model and try out different learning rates, try out different optimizers. How can we make it easy to scale out one model that you've developed and run many executions of those with different hyperparameters? Once you have a model that performs the best, we also make it easy for you to ship that into production. There are different paths to production. For a model that runs during the web request for serving a ride, it needs to be served as a web service. Other models may do some kind of offline prediction on a daily basis or on a weekly basis. For example, figuring out the right population to send out an incentive to. There is a third type of inference, which might be a machine learning model running on the edge, for example, in an autonomous car. So how can we make it easy across all these different types of deployments for research science to go through this life cycle of model development, training, and production? So research scientists spend a lot of time doing non-modeling tasks today. If the audience is full of people who are building their own models, you might realize you spend a lot of time collecting the right data set, querying it, filtering it, slice and dice it to generate the correct training data. And then if you're training really compute-intensive models like deep learning models, you need to be able to provision the right hardware for your model. You might want to run many different iterations of those models. You need good logging and monitoring. And our team's job is to make all of that simple. So I'm going to get into some of those requirements to start. We wanted to build a system that's framework agnostic. The current landscape of machine learning is so rapidly changing. There are some really great frameworks like TensorFlow, PyTorch, that have come up in the last few years. And then there is the whole scikit-learn ecosystem, or boosted trees, any new libraries that might come up. So we want to support any arbitrary framework and not be tied into an implementation for a specific framework. Support for GPU workloads. Almost all deep learning models are extremely compute intensive, several orders of magnitudes more than traditional machine learning approaches. And we want to serve those internal customers to Lyft who are training very large-scale models that feed imagery or video data and can have model training that can run for days. How can we make their job easier and support single GPU, multi-GPU, or distributed training workloads? We wanted the system to be cloud agnostic. And the main reason for that is, along with the software ecosystem, the hardware ecosystem for machine learning is also rapidly evolving. A study by OpenAI shows there's almost a 10x improvement year over year in ML compute performance, which is extremely fast. And there are custom accelerators, ASIC-based model training systems that are being developed. NVIDIA has the Volta GPU, which is the current state-of-the-art GPU for model training. However, Google's working on TPU chips that are custom ASICs built for model training. And we wanted to be able to leverage any of this hardware because we cannot anticipate exactly how this ecosystem is going to move. So we wanted to be cloud agnostic. Now, with a lot of power comes a lot of responsibilities, right? However, we have many levels of users. We have researchers who come from an academic background and don't really want to deal with a lot of infrastructure problems. They don't want to get into the nitty-gritties of how certain infrastructure is set up to launch their jobs. However, for some advanced use cases, such as distributed training, or if you want to build custom ops for your TensorFlow model, we also have very advanced software engineer users who want to get the maximum flexibility around defining their models. So we wanted to support both such use cases. So we decided to use Docker containers as our primary abstraction for most of our jobs. This solves a lot of problems around dependency management. It makes it easy to be framework agnostic. As long as you can package your code into a Docker image, you can run it on our system. Now, with containers, we need to decide a good execution engine for those containers, and the Kubernetes ecosystem has really blown up in the last few years. Kubernetes provides a very rich set of APIs for launching very complex workloads. You can scale out very easily using Kubernetes on any of the cloud providers. It provides a cloud agnostic API for us to launch jobs, which can then translate from either AWS to Google Cloud to any custom deployments. It handles a lot of different infrastructure challenges that we would have to design on our own. And I'll get into some of the details. One of the challenges with using Kubernetes, however, is its power. It is very complex. There's very low-level APIs that most users may not want to deal with. So I'll show how we create the right abstractions to help our users launch all kinds of workloads. We decided to go the route of providing an easy path that is fully UI-based. So we have our own UI-based system. Internally, we call it Lyft Learn, that allows a data scientist to go from developing in Jupyter Notebooks to containerizing their models to running very large-scale HyperParameter Search and then deployments. However, for advanced users, we provide a much lower-level API using command line to give them full flexibility for defining their machine learning workloads. So let's go through some of those features. notebooks. This is the entry point to any researcher's machine learning development flow. You want to have an interactive environment where you can easily query data sets, build out different stages of your model development, and try it out. And Jupyter is the de facto standard right now for a lot of these model developments. So this is Lyft Learn. On the left side, you see the different functionality we provide. And the first functionality is environments, which are Jupyter environments for developing either Python or R models. We're moving quickly towards Python as our standard programming language for most workloads, just because it provides us really great end-to-end integration from development to productionizing. So in this environment, I can quickly pick a software environment that I would like to launch. So we provide some pre-baked software environments. Here you can see I have 4 different environments. One, which is the standard Docker image containing most of my commonly used Python libraries. And next to it is a deep learning plus TensorBoard image. In the standard image, we only launch a Jupyter notebook. However, with the deep learning image, we can launch both notebooks as well as TensorBoard. TensorBoard is a visualization tool that TensorFlow and now PyTorch use for measuring your learning performance over time. Similarly, we allow different teams within Lyft to provide their own software environments in the form of Docker images. So if you care about a certain set of requirements, which are different from most users, and you want to pin different versions of scikit-learn or use a RC branch on TensorFlow, you can do that and provide that as a custom environment right here. Next, you pick the hardware resources you want to run this job on. So we provide some pre-configured hardware environments. You can choose many different configurations of CPU, memory, and GPU that you would like for your job, for your notebooks. Having some fixed environment choices makes it easy for users to quickly go through this flow. However, you can use the command line tools to arbitrarily create any kind of environment, which translates to Kubernetes resources behind the API. So you click next, and now you have a new environment set up for you. Now you can see we already provide a link to the notebook right there in the UI. You click on it, and it'll take you to your Jupyter environment, where you can start developing your models. In the background, these are some of the links that are available to you once you launch the job. You have the notebook interface, where you can develop any model, and you have the TensorBoard for visualizing any model training that you might be running on it. In the background, we're creating Kubernetes objects, the primarily one being a pod. Pods are the lowest execution units inside Kubernetes, and you can configure many different containers to run inside a pod. So here we're launching a pod with a given set of Python requirements, along with the right resource requests that the user submitted. It picks up a certain image, but you can using it as a Docker image gives you full flexibility to pick the image you would like to run. Along with the pod, we attach certain volumes. A volume can represent either a temporary disk space the user might want for loading some data sets or generating some training artifacts, such as checkpoints, intermediate checkpoints for your models. We also mount NFS into these pods. So we have AWS EFS, which we mount as a persistent volume on each notebook. The primary use case there is a user can just start a new notebook, start developing a new model, save their notebooks on the EFS, and once you're done, you can terminate the environments, come back again next day and start where you left off. So it makes good use of the resources by letting you checkpoint all your work and come back to it later, at a later point. We also provide GitHub-based integration. So let's say you've done all your iteration and now you want to push this code out for review. Then you can log into GitHub from your notebook interface directly and push it out as a new pull request or as a new commit. We also launch services and Ingress. These are other object types in Kubernetes, which allow you external access to any Kubernetes links. So in this case, my notebook URL is actually a Kubernetes Ingress backed by Elastic Load Balancer, which allows any user to access the notebook over the internet. So what are some of the challenges we faced while building this? Some of these machine learning images are extremely big in size. On average, our notebook images are between 12 to 15 gigs in size. And just downloading, because it contains CUDA drivers, it contains the whole CUDA toolkit, it has all the binaries for TensorFlow, PyTorch, supporting Python 2 and 3, and all other frameworks that users might want. So loading a new job can become a bottleneck because it might take a long time to download these images. So what we do is we create a warm cache of images, commonly used images, on every single node on the Kubernetes cluster. That's one of our approaches for pre-caching most commonly used images directly available on every single node. This helps us eliminate half of our boot up time. Our Kubernetes clusters are also auto-scaling. So based on unfulfilled capacity, unfulfilled requests, the Kubernetes scheduler can scale up the number of AWS instances that are needed to fulfill those requests. However, that itself, starting a new instance can take a while as well. We use Packer, which is a packaging tool, open source packaging tool for generating AWS AMIs or many other types of images. This helps us create the VM image pre-baked as it's needed to launch on AWS. And it cuts down our, in the original Packer builds, it cut it down from 20 minutes to 6 minutes or so. So we combine, there's another thing we need to do, which is for notebooks, you want the experience to launch a notebook really fast. However, launching a new node can take up to 6-7 minutes. Downloading the image, if it's not pre-cached, can take 10 minutes. So we solve both of those problems. We create a warm cache of extra nodes available for both CPU and GPU types, and that's a configurable limit. So Kubernetes provides a great construct called priority classes, which we can use to create lower priority jobs that can be preempted with real workload. This allows us to specify extra capacity for jobs that are just sleeping around, and they're just waiting to be preempted by real workloads. This allows us to make the notebook experience extremely fast. We're able to provide consistent notebook launch times within 10 seconds for these 15 gig images on Kubernetes. This makes the data science super productive, and that makes us happy. So remember I mentioned how your notebook code is residing on NFS. However, in order to productionize something, we don't want to rely on some code lying on NFS as our main source of truth. So we provide good GitHub integration. Just from the UI, a user can go and set up their GitHub credentials. They can go to GitHub, generate a new token for their account, and register that in the credentials page. These credentials get translated to Kubernetes secret objects. The Kubernetes secret objects it's a construct in Kubernetes to allow you to store arbitrary secret data in encrypted format on the backing data store called etcd. These are encrypted at rest, and they can be mounted as part of any job that gets launched on the cluster. So once you set up your GitHub token, Once you set up your Hive credentials, once you set up your Presto credentials, then we make them automatically available on your container during any notebook or training job creation. So you can access external data source for retrieving your training data sets. And the same way, the credentials are used for publishing new code into GitHub. So GitHub token is a form of credential, but access to Hive can also be another form of credential, and these are all configurable. All right, so let's talk about training and deployment. Once you've developed your model and you just want to try out many different variations of a model with different optimizers, a different learning schedule. Let's say for deep learning models, it's very common to try out different number of iterations for the mini batch training. So it involves a lot of exploration, and we want to make the exploration really fast. And all of these jobs can run in parallel. You could launch hundreds of jobs with different learning rate or different optimizers or any other parameters, hyperparameters that your model takes. How do we do this? We create a really simple contract for users to implement. So as a research scientist, your notebook just needs to contain a model class with no extra imports or anything. You just need to have a class named model and a bunch of methods which will automatically become your entry points for different types of jobs you want to launch. So let's go through all of those. So here's my model class. And the training method, I'll go into all of these in the future slides, actually. From the notebook also, we provide a custom plugin which allows you to take your notebook code along with any other code around it from that base path in the NFS folders and package it all up as a Docker container. So as a data scientist, I don't need to deal with any kind of CI. I don't have to deal with involving an engineer to convert my code and package it to a Docker image. I don't need to understand how Docker files are written. I just say, hey, by the way, here's my model. Here's my logical name for that model and a version. Now go build a Docker image with that. And users can pick a base image that they want to put their code on top. These base images represent certain Python package dependencies. So let's say you're using TensorFlow in your model and you want to use a base image which has CUDA drivers for GPU execution and a certain version of TensorFlow. So you can pick that base image as your importing image in your Docker file, and then basically layer your code on top of it. So for a user, all they have to do is click a button to generate Docker images. We use Docker in Docker by running a Docker process inside Docker on Kubernetes pods to build an image and then push it to a registry. All right, so let's get into the details of this model contract. It all starts by initializing a model class with a default set of hyperparameters. So we automatically detect hyperparameters set up on a model based on the hyperparameters dictionary mentioned over there, the list mentioned over there, where you define what are the default hyperparameters, what are their default values, and during job launch, you will automatically get a chance to override these values if you want. The train method becomes your entry point for any kind of batch training. If you define some default hyperparameters and you want to run 10 different versions of those with different values, then it will invoke the training endpoint for that. We'll get to the UI. Let's go back. You see the training tab over there? So using the training tab, you can just pick a model that you defined through the Save Model button, and you can invoke a new run offline for that model with overriding certain hyperparameters that you care about. And that, in turn, invokes the train method out here. Now, we provide two types of predictions for your models. Let's say you trained a model that performs really well, you're happy with it, and you want to generate daily predictions from that model. Every day, I want to predict a driver's likelihood of driving at a given hour, for example. If I want to generate that, I can do that offline. It doesn't happen in real time. It's an ETL job. So the ETL job will just call Lyft Learn API with a batch predict call, which will run the batch predict method as your entry point for your model. So you can do different things, and you have the different endpoints available for those. Similarly, if you want to run web services on top of your model and make it available as a web service for real-time inference, you just create a predict method in your model class, which takes a dictionary of data features as inputs. So if user defines the predict method, we would automatically run a gunicorn and Flask server on top, which starts serving the predict method at a canonical endpoint / invocations. So as a data scientist, still no engineers involved in the process of taking your model from development to either offline prediction or to web-based prediction. And these tools make it extremely fast for any user to go from idea for a model to running it as a product feature. What's the init predict method? The init predict method is useful if you want to do some kind of heavyweight initialization for your predictions. For example, you might want to load model checkpoints from S3, and that might take a while. So the init predict method is called once at the initialization of your prediction job. That allows you to do some heavy operations, create an in-memory state, and then run many predictions really fast. If you look at this contract, it's extremely generic. We're making no assumptions about what kind of training job is running, what kind of predictions happening. We're just providing hooks for a user to run these jobs at a given schedule or manually through a UI or through command line. We also provide easy command line tools for users to build Docker images locally with their models and push it into a dev registry from where they can start using the same features from the UI moving forward. HyperParameter search. So far I've talked only about manual hyperparameter search. User is specifying either through a Python script or through the UI many different runs of jobs they would like to launch. However, for certain models like XGBoost or any kind of boosted trees, you have very large number of hyperparameters, and you do very large exploration studies across those kind of models. Those explorations can yield real significant improvements to your model. So for such type of models which require very large-scale iterations or experimentation, we integrated an open source tool called Katib, which is part of the Kubeflow project for automatic hyperparameter search. So a user can perform many different types of hyperparameter search, like giving us a grid of values. Let's go here for an example. So you can define different metrics you would like to optimize, and you specify either a range or specify it as a numerical value with some kind of step count, or it could be a dimensional value with many values for those. And once you specify those, you can also specify what kind of instance you want to launch these jobs on. So you can pick, is it a high memory instance? Is it a GPU instance? Is it a 4 GPU instance? And we're working on adding a cost limit where users can specify how much money they're willing to spend on these jobs. So the study will automatically run many different iterations of these models by using different combinations of hyperparameter values and listen to metrics being emitted through each of those jobs in terms of the final performance metrics for each of those jobs. And then a controller will make the decision on how to tune certain hyperparameter values in the direction where it performs better and better. So it's a fully pluggable strategy which allows for choosing different kinds of controllers. Either you can use a really dumb controller that just takes a bunch of different hyperparameters and runs every iteration of those. Or it could be more like a real optimizer, machine learning optimizer, which can try to optimize all these values based on, it's going to try to fit the values to find the optimal hyperparameter values that perform the best. It kind of looks like this. This is the UI that comes with the Khatib project, which is a implementation of Google's automatic hyperparameter search system called Vizier. It can trigger a very large number of iterations on Kubernetes and listen to the metrics that it's trying to optimize, and based on that, define the next set of hyperparameters to launch. We've seen really big gains in terms of data scientist and research science productivity from using these tools, because that can automate the process of discovering the right hyperparameters, which can take several days if you were to do that manually. You don't have to keep track of all the different job states if you were to launch them manually. You don't have to handle failure scenarios. The controller takes care of all of those. So scheduling. So I spoke a little bit about batch predictions, and the way we integrate this is through triggering the Lyft Learn API on a schedule using external schedulers. At Lyft, we use Airflow heavily, which is a very successful open source scheduler. And we've provided custom operators inside Airflow, which hit the REST API for Lyft Learn on a given schedule and execute certain models. We also have some other internal schedulers inside Lyft. And since the REST API for Lyft Learn is the primary interface to all the functionality, it's really trivial to integrate with any custom scheduler we decide to use. Some of the future work. We want to do better integration with GitHub so we can have stronger code review. If a model is developed, we want to be able to hook into Git PR review process more deeply, so we can track what a model what's the code running for a given model running in production. We also want to expand and make it easy to create custom environments for your notebooks. Let's say you just care about certain types of libraries that no one else does, but you want to quickly start using the whole functionality of the system. You can do that. We want to make it easy for users to register new base images. The way we've designed the system is we have the API layer that is highly pluggable, and you can push new images that you want to register as software environments, or you want to push new hardware configurations as your hardware resource options. Users can also, basically, everything underneath is Kubernetes for execution, and it has a database that stores some metadata about historical job execution. So Kubernetes is not very good at storing very large amounts of historical state. The etcd data store is more designed for current workload. It's not designed as a data storage system. So we use a Metastore Postgres database for storing historical runs, their status, what kind of hyperparameters were submitted in order to run a certain training job, so that any user can replicate a training job that was created anytime in the past. So by capturing metadata about model execution and running it all on Kubernetes and using Docker abstraction, we have the ability to replicate the models any number of times you want. And so that prevents a lot of errors in machine learning commonly seen around not being able to replicate a certain result, or the data changing underneath, or the model code changing over time, affecting model performance. By containerizing those models, we freeze the state of the algorithm that was run in order to produce a certain result. We're working on open sourcing this so that it can be available to a bigger community. If anyone's interested, definitely reach out to me in the office hours. I'm happy to talk more about it. Thanks for listening. Yeah.
Do you still have people at Lyft running notebooks locally, or has this just been like presented itself as the most obvious solution for running notebooks anywhere, and everybody's all in on this?
So in the very beginning, we launched the very first version of this system in May, and earlier people were still hesitant because they had a very well set up environment locally. They didn't have big data sets. They just sampled it enough where they didn't care about having a remote system. But very, very quickly, the adoption has been insane. Like we have like a very high NPS. Almost 80–90% of the research scientists use this system now, because when they finally switched over or tried it out for their near use cases, they realized that they can get a huge amount of power unlocked, because you get persistence of your code over time. You can get any arbitrary machine configuration very easily. Your code is actually shared through NFS across all your instances, so you can develop on a smaller instance, but then you can scale out on very high memory or multi-GPU instance. So that kind of flexibility, like people really love it, and they don't have to worry about closing their laptop and losing the state. All those problems are gone. So it's kind of eliminated the need for local development completely. We also provide code syncing tools to make it easy to develop in your favorite editor, and then just continuously sync your code into the Kubernetes pods. That was one of the big asks that was blocking a lot of people. Not everyone cares about developing in Jupyter Notebooks. They want to be able to use their favorite editor. So that was, I guess, like one of the biggest features that moved people away from local development.
Other questions?
Yeah, thanks for the talk. I was curious, do you have also engineers using this, or is it just data scientists and those kinds?
Yeah, that's a good question. So as I said before, we have multiple layers, multiple tiers of users. The researchers are less programming oriented, they care about the machine learning problem more. They don't want to get into details. So the UI solution is used heavily by the research scientists. The engineers seem to prefer to use command line tools. So we have a ton of engineer users. I think that who use command line tools more than the UI. One other thing is, in Lyft, from the beginning, we've had a distinction between a software engineering role and an ML role. So those distinctions are getting more and more merged now. They're going away. So we see more engineers using the ML tools now. Yeah.
So do you still have like a productionization step where like there's the development of it in a Jupyter notebook, and it seems like this could actually like automatically spin up a service that could then be hit from production, but do you still have like people taking a model developed by the ML researchers and like productionalizing it to make it faster?
I think that's a common problem we were seeing a lot in the past. We actually have the ability to directly spawn a Kubernetes deployment based on the model you generated using and it calls the predict method that I talked about earlier. However, we're kind of putting on the back foot and trying to better integrate with CI and Jenkins and deployment pipelines. So we have good traceability of what code's running for a web service, and how to roll back or being able to inspect what's running inside that code. So we want to tie it closely to GitHub commits. So right now, our way of doing that is just data scientists will push the code to GitHub, and we're working on making it really easy to use the CI process at Lyft to launch production services from that. And we generate automatic monitoring, and we manage the SLA for rolling out those models. Yeah.